Welcome again. In the previous video, we just realized that our coloring method, is not very efficient. I mean, it works. Obviously, we were able to figure out the 6 coloring patterns up to rotations and reflections, but, well, the formula that we created, this formula, there are too many colorings, like too many summons that we have to go over, right? So in this case, 16 of them, 1, 2, 3, 4, all these things. So this is too much work. Instead, I propose, well, actually Burnside proposed another method. So let me first write down this method. So let me use my definition here. So I will call this the Burnside Lemma. So the number of distinct orbits, in that case, number of orbits equals 1 over g. However, the summation, be careful on that, is the summation over the group itself, not the colorings. And we are summing all these fixes. So that's all colorings that are fixed under a given group member, or symmetry, you can say, where formally you can write that fix of a group member is equal to all the colorings x in x, such that our group acting on that coloring will give the same coloring pattern. That's pretty much the lemma itself. Now, this lemma is extremely powerful. Before I apply it to our problem at hand, I want to provide you a sketch of the proof, which is obviously you can find it on any good combinatorics textbook. So we can put our colorings as the columns, xj, x n, and colorings. In our example, it would be 16 different colorings, and the group members g1, g2, gi, gm, m group symmetries. And in our example, in the 2x2 chessboard example, that would be 8. But now look at it. When we use the summation over all elements, colorings, we basically summed over all the columns, right? So in this table, so okay, so let me step back. So let me first make something clear. So let's assume that in this matrix I will place a check mark. For instance, in row I, column J, I place the check mark to identify that G sub I acting on X sub J gives you X sub J, the same coloring again. So now the whole task is to add up all the check marks in this matrix. So one way to do it would be obviously to sum across the columns. So you find the sum for the first column, for the second column, and so on. So the sum of check marks for the first column will give you the stabilizer for x1, for the second one x2, and so on, x sub j, x sub n. And you add them up. And once you do that, you know what you will get: the summation over all colorings of your stabilizers, x sub I. Instead, one would immediately realize that we could have done the counting of all the check marks in another way. It would have been basically counting the number of check marks in each row and then adding those counts. So basically the number of check marks in the first row is basically the fix of G1, and the second row fix of G2, and so on, the fix of G sub I, and the fix of G sub M, and adding those up will give you, so adding all these things up, summation over the group members, the fix of G sub I, so G sub I in G, and adding up all these numbers will, so these are essentially the same thing. So this is kind of a nice application of counting in two ways, a very well-known counting method. And this is, as I said, just a sketch of the proof, so you can fill out the details of the proof. But that does the trick. So now we can go back to our problem at hand. So let me create a new page here and solve the problem for our problem. So the number of orbits again in the 2x2 chessboard coloring would be equal to 1/8. That didn't change. We still have 8 group symmetries here, 4 rotations including identity and 4 reflections. And then we are summing, okay, so we need to sum the fix of E plus the fix of, well, the number of elements in that fix. The fix of A plus the fix of B, and so on. All these group members. Okay, so how many colorings would be fixed under the group action of E? Well, E is the identity. The identity would fix every single coloring, right? So all 16 colorings are fixed under E. Now let's go to rotation. So which colorings will be fixed if A is applied to those colorings? For instance, if A is applied to C2, would C2 be fixed? No, because A applied to C2, if you rotate C2, let me remind you, C2 looked like this. And if you applied A to C2, you would simply get, I apply A to C2, I basically get C3. So that won't work. So how many will be fixed under A? Well, those that are fixed, if you remember, were those that are fixed under A are simply C1 and C16. So there are 2 that are fixed under A. There are actually 4 that are fixed under the 180-degree rotation, right? So what are those 4? I believe it would be, so it's not surprised that this one is fixed under, I'm talking about under B. This one is obviously fixed under 180-degree rotation, and then the blank one is fixed, and all 4 filled with black color is fixed. So those are the 4. For C we have 2. For the reflection across the horizontal axis, I believe we should have 4. Go back to our table and you will see that. And finally we have 8 for the 2 diagonals, each one 8. So you add these numbers, you get 48, and 48 divided by 8, you get the same answer. But now notice that this is much more efficient, much faster, because you just make your calculation based on the number of orbit members, right? So that's quite effective. So as a formula, let me just remind you the Burnside Lemma. Yeah, so what I'm meaning is that this is much less than doing it over all potential colorings, which can be in great numbers. So let me stop here, and then I will solve several more applications of Burnside Lemma to make the concept clear to everyone. So that's all for this problem now. So we are done.